Okay, so the we really only have one topic to go here. We're going to be doing about two half kind of units, and one of them is a bit of an introduction to differential equations. It's, of course, a huge topic. I think I've mentioned this before, but it's a huge topic if you were going to go on and study those poor folks out there who are going to do something like engineering. But solving differential equations, we're just going to take a look at some basic cases, and today we're going to focus on growth and decay for this first part of the lesson. So, I mean, I don't think... at the moment anyways, this needs to be, I think we're good with the notation, but just as a refresher here, that when we say dy by dx, we could also mean y prime. I think we've seen that. The other thing we could rearrange this as is that would be like whatever my derivative is times dx. And the reason that we're going to be going that way is if I rearrange things this way, I'll be able to integrate and solve a differential equation. So what it looks like is easier to show you an example. For example, in this first one, what I would want to do is rewrite this as dy by dx. That notation is more helpful to us when we work with differential equations, because what I'm going to do now is I'm going to move some things around so that I have y dy equals 2x dx. So basically what I've done is across the equal sign, I've been able to split up this equation in terms of with respect to y and with respect to x. So all I need to do then to figure out where this originally came from would be to integrate both sides of this equation. And what I'd come up with is y squared over 2 equals x squared plus a constant. Now, of course, you know, we try to simplify as much as we can and where we can, but at the very least, I think we would probably write this answer down as y squared equals 2x squared plus a constant. And now, there's that funny math about the constants. You know, 2 times a constant is still a constant, so it just turns into a constant. That's, I, on purpose, have left out the 2c, right? So when I multiplied both sides here, 2 times the constant will still be there. And I'm bringing it to your attention because when you check your answers over tonight in your homework, you're going to see the textbook does that too. Constant, just leave it as a constant. Okay, so I'll let you think about how would you solve the next equation and see what you could do to separate so you have one side of the equation with respect to x and one side with respect to y. So I'm gonna start working on this, but I think I'm gonna need more space, so I'll move this to another slide. The clarity is always better too, of course, when I can write it for you on one nice big slide rather than cramming it all in there. So if I was to rearrange this, so far the only strategy we've talked about is trying to keep one side with respect to x, one side with respect to y. And it would look like this then once I have everything set up. Okay. And at this point, I could then go ahead and solve by integrating both sides. Okay. So if I integrate both sides, what will I come up with here for the side with respect to y? Yeah, it's a natural log. So it'll be natural log 1 plus y equals x squared over 2 plus some constant. And now we can actually separate this in terms of y and get y all by itself. How could I do that? Like right now, y is locked up in a logarithm. How can I unlock it?
Do a barrel roll?
No ideas?
Do a barrel roll.
Stop. Any other ideas? Do you remember in Math 12 what we would do for this? If there was an equation like log, I don't know, let's say it's log base 2 of x equals 3. How do you get rid of, how do you take x out of the logarithm? Yeah, you can rewrite it. So in this case it would be, now the log is gone and you've taken it out, right? So, well, it's a good thing that we talk about it then so that it jogs your memory. In this case, the base is e, so when I rewrite it, it's going to look like this. It's going to go e to the x squared over 2 plus some constant is 1 plus y. Okay. And if I rearrange that for y, maybe I'll do it, actually there's enough room there. It's going to be y equals e to the x squared over 2 plus some constant minus 1. Now, this would be correct. However, it's probably not what you're going to see in the textbook. What you're going to end up seeing for the answers, and not just our textbook, but in general, is that the answer would look like this, and it's not always obvious because a few steps have been skipped in order to get here. So when we skip some steps, let me show you what happened. If I go and I redo this, so maybe I'll pick a different color. What I actually did was I went e to the x squared over 2 plus some constant. That's the same thing as e to the x squared over 2 times e to the c if I use the exponent laws from way back in grade 10. Okay? E to a constant, this is that funny math that kind of confuses you. What's e to a constant? A constant. Yeah, so this here is just some other constant. So this would be the answer you'd find in your textbook, although you would have been correct in your work. So again, I just want to bring that to your attention, the way that the constant is used. Okay, so this would be the answer. We would leave this as the general solution. We'd have to know something about the original function in order to recover the constant. So the next thing we're going to talk about is the formula that you saw in Math 12 for growth and decay, like the title is here. But we weren't able to show you in grade 12 where it comes from because you didn't know calculus, obviously. I mean, look how far you've come, right? So at this point, things which are a differential equation like this, I mean, it doesn't look obvious, but what we're saying is that the rate of change, so maybe it'd make more sense if you wrote it like this, is some constant times what you currently have. So it might be a population, it might be money, it might be temperature. So let me give you an example. I'm going to put the example in here, but I'm going to write it, bigger on a new slide for you. But for example, what are some things that do this? Well, let's just say, can somebody come up with a sentence that would describe this? You were all at the assembly this morning, right? Some of you, I saw some of you there. So what would be a sentence that we've just done here? Yeah, Robbie?
The interest on 1,000 with...
Yeah, that's enough. What's the rate?
5%.
Yeah, so this is like you start with $1,000. That's how much you currently have. And the rate of change is proportional now. The next step, this is what you now have after you've multiplied by 1.05. Right? And we could do this quarterly. We could do this semi-annually. And in calculus, we're looking at it continuously. So that's what we're going to find here is the continuous growth formula for Math 12. So what I'm going to do is I'm going to show you where it comes from. It's solving the differential equation that I had. So for example, if I have y prime is ky, then this is the equation I'm trying to integrate. So I would end up with, whoops, wrong letter. I would end up with, let's see here, k dx. And now if I integrate both sides, I'm going to end up with natural log of y equals kx plus some constant. And we're going to rewrite just like we did before. So it's going to become e to the kx plus a constant is y. And as I just explained, that's going to give us a final answer that looks like this. So this is the formula. It's a little bit disguised. When we dealt with it, it looked like this. We said some amount is what we started with, and we went e to the kt. But these are the same. We've just changed the letters around, but they're the same formulas. That's where it comes from. And that's what we're going to practice for the rest of the lesson today, is using this. I've already solved the differential equation for you. You have the formula, and you know the formula for Math 12, but we're going to work on using the applications for it. Am I in the way? Here, I'll just... All right. So, of course, you should recognize that from Math 12. But let's try and find, first of all, this example. If you were given 2 points, this is a strategy that you're going to be working with usually, is you're going to take 2 points and use it to find the missing pieces in the model. So those are the points that I have so far. And here's my model, y equals c e to the kt. So if I take a look, this point is very convenient right here because there's a 0, which means if I substitute that point first, what I'm going to end up with is 2 equals c e to the 0. So c equals to 2. So that way I can get my constant very quickly. Now how would you say this as a Math 12 student, right? Like, what does that letter c represent?
The constant.
Yes, it represents a constant. Thank you. But, you know, it may need some time to jog your memory. That was the initial population or the initial amount, or that's what's going to grow. So at time 0, we started with 2 things. So that's what the constant represented here is. That's the initial amount, just like you know from Math 12. Okay. So now I have a model that looks like this, which still is not one I can use because I don't know what the value of k is, but I haven't used this value here. So we're going to find the value for k by substituting the second point, and that second point is going to then be 4 equals 2 e to the 2k, and I have to rearrange this to solve for k. So to do that, I would get 2 equals e to the 2k, or the natural log of 2 equals 2k, and k would be natural log 2 over 2. So it's a fairly large value, 0.3466. So now when I want to figure out what will the population or whatever this is be at time 3, I now have my complete model, which is y equals 2e, and I'm going to put 0.35 just to abbreviate it here, 0.35t. But remember, you don't want to round this. You want to leave it in your calculator as the full value so that we don't get the rounding error. So 2 times e to the 0.35, and we're going for 3 at the time. So now there's going to be, at t equals 3, there will now be 5.66. So I'm going to let you guys, actually I'll start the first one with you, but then I'm going to let you guys try to do the same thing just for your own practice. The next example, half-life, which again is something we dealt with in Math 12, but this time we're using the continuous version of it. So we need to come up with, so far our strategy has been let's use 2 points. So can anybody come up with, when you read that initial information there, can you come up with maybe 1 point for me? Good, yeah, that's the one you want to grab right away because you start at 10 grams, so one of the points you get would be 0 and 10. Can anybody come up with, maybe find a creative way to find another point? You can, you just have to think a little bit more about how you could use the information. Oh. Now I have to ask you because you laughed about it. I'm sure you can do it. Oh, because you can't read it? Sorry. Well, I'm still going to pick on you, but it says, maybe I'll zoom in and see if this helps. It won't fit. Okay, but it says 24,360 years is the half-life. So how much plutonium, whoops, that's too big, sorry. How much plutonium will there be after 24,360 years?
5.
Right, see, you can all do it. It's that after one half-life goes by, 24,360, you now have 5 grams of plutonium. So you do have 2 points. Okay, so it's your turn. See if you can work out the rest of the model. Once you've created your model, how long will it take until there's 1 gram remaining? Okay, so I'll try to create the model that I have. I'll use this first point, which you're going to see that it's not always in your best interest just to throw the numbers straight in. You actually do want to double check. So you can really quickly check that this constant is 10 just by substituting in the, values, and you'll see shortly why it's important that you don't rush it. So the constant equals to 10. Then that means my model now looks like this, and I have to figure out what this continuous growth rate is. So I'll substitute in 5 for y, and 24,360 for the time. And that means I'll get 1/2 is e to the 24,360. Let's see here. Let's switch this for a second. So the natural log of 1/2 will be equal to 24,360k. So that gives me a value for k. If I put it in the calculator, it's going to be fairly small, but let's see. Natural log of 0.5. So I get about negative 2.85 times 10 to the negative 5. And you're going to leave it in your calculator. You don't want to round it. So the model I now have is y equals 10 e to the negative 2.85. Sorry, negative 5. Oh, that's messy. Let me try it again. So we add to the, oops. Try that one more time. So it should be to the negative 5 and then time. So when there's 1 gram remaining, that means I'm going to need to figure out where there is 1 equal to 10 e to the negative 2.85 times 10 to the negative 5 t. So it's going to involve the logarithms the same way it did when we solved for finding a growth constant here. So I'm going to get 1 out of 10 is e to the negative 2.85 times 10 to the negative 5t. It's up here, it's the growth constant, that's the number. So you have to start here and then solve for k. That's where it came from. Well, natural log is the log in base e. So e comes from...
And where does natural log come from?
Because in order to solve for this exponent right here, I have to use a logarithm to get the exponent out of the equation there. Okay, so then I'm going to have natural log of 1 out of 10 equals negative 2.85 times 10 to the negative 5t. So time will be like this. So natural log of 1 over 10. So it's only going to take 80,000 years to do that, so not very long, almost 81,000. Hence some of the controversy around nuclear energy. Okay, so that's pretty standard as far as the growth and decay models go. Can I move this down? Okay, so let's have you try doing a couple here with your neighbor. So these next two here, the first one is a manufacturing plant. Just to be clear about the question, in case the wording is difficult, let's say that the sales dropped from 100,000 units to 80,000 units a month, and that happened in a 1 month time span. So this is like month 0, and this is like month 1. And after 2 months, so
Like 2 more months?
that's what I'm clarifying. So this would be month 3 now. Okay, just to clarify that. It looks like most people are just about finished the first one, so I'll try to catch up with what I would have done here. You can start on the second one if you're already finished. So the initial population is 100,000. So that means I'm going to have a constant for 100,000. So I think I'll just put 100 to abbreviate that. And it says the second data point I have tells me that 80 is 100 e to the k. So that way it's going to be 0.8 equals e to the k. So natural log of 0.8 is equal to k. So the model that I now have would be y equals 100 e to the natural log of 0.8 times the time. So if I wanted to know at month number 3, then I'll have to substitute in for time 3. And I'll see what that's going to give. That's 100 e to the natural log 0.8 times 3. So I get about 51,200 will be the, wow, you don't want to work in that factory, wow. So anyways, we should have about 51,200 there. Could somebody verify that they also,
Yeah.
okay, thank you. So next one here is a population of fruit flies is growing exponentially. Here's the information you've been given. However, this time there is a small twist, and if you can still work it out. I'll give you a couple strategies, but you're not told the initial population. It says there's 100 fruit flies after the second day and 300 after the 4th day. So you know about this on the second day and on the 4th day. Anyways, I'll let you talk it out with a neighbor, but then we'll talk some strategy in a minute. Okay, so was anybody able to figure out what they could do to get around this? Divide? What do you mean by divide? Yeah, so that's one strategy. One strategy is to take the information that you've got and say at time 2 there are 100 flies, so you end up with 2k, and then the second time I do this, I've got 300 fruit flies e to the, what was it, 4. So what I could do is, the reason I can't solve is I have 2 variables, but what I can try to do here is say that now I know what c is equal to, and I can put it into here, and I will end up getting rid of, I only have 1 variable left. So that's one way it could work, which was kind of the hint that I gave you. But there's another way which is a little bit more common sense, and basically we're going to translate this graph. So by translating, I mean move it left to the or right. So did anyone have another strategy maybe? Well, what I mean is, it would be really convenient if the second day was the first time, right? It would be nice if they said it started with 100 fruit flies. So what if we just said, okay, well, let's assume it starts with 100 fruit flies. Well, what are we looking for then? Well, we're looking for 2 days before, so we're looking for time at -2 if we did that, right? So it'll still work. I'm going to work it out that way just to show you how it would go. Okay, so let's say that instead of the second day, we're going to move this to be day 0. And then what day would the 4th day be? Right, some of you. And no comment, anyway. Right, we're basically shifting everybody over by 2 days. We're taking the graph and we're moving it, we're translating it. So that means we're now looking for the initial population would have been day -2, right? Everybody went backwards 2 days. So this is the equation I would have gotten. So it would have been here. And I can use my other data point, which remember is no longer on day 4 according to this. It's now on day 2. So I can solve for this and get 3 equals e to the 2t. Natural log 3 is 2t. So t is natural log 3 over 2. So my model is this. Sorry, yeah, it should be a k. We'll just do this. Close enough. Equals natural log 3 over 2 times the time. And that model, if we're using it, we're now looking for the initial population, which is no longer at 0, it's now at -2. So I'm going to put in 2 days before that. So -2 is the value. And we're all going to end up, I mean, regardless of which way you did it, we should all end up at the same place, which I'm trying to jog my memory while I do this. I thought it was around 30 something. Let me... $33 1/3, so I guess there'd be 33 fruit flies if we rounded it. All right. So far it should be fairly, I mean, with what we've been doing, it's a lot like Math 12, only you have to come up with the formula all by yourself, instead of being given a formula to work with, right? You're creating your own model. But this next question is identical, yet very different. So I want to walk you through it, and then it makes more sense to talk about it once we come up with this model. So suppose that a room is kept at a constant 60 degrees and a cup of coffee with temperature 100 degrees is placed in the room. Newton's law of cooling dictates that temperature will change with an exponential model of decay. So basically the temperature in the room is continuously eroding by a proportion, like a constant of proportionality. How much you have now, maybe it takes off 97, or maybe it takes off 2% every instant or whatever it is, right? So it says if the coffee in 10 minutes is now 90 degrees, how long will it take before it gets to 80 degrees? And the hint I'm going to give you here, it'll make a lot of sense once we've done this, why I've given you this hint, but the equation that you're actually working with is this differential equation. Okay. Why is that? Well, and if there are any physics nerds out there, technically you can never actually touch 60 because you introduce more energy into the room. So by conservation energy, anyways, never mind. But if you can never touch 60, what does that sound like to you if we were to say, what else is when we can't touch something? An asymptote, yeah. It's a lot like an asymptote. So if we were to think about what's going to happen in this graph, I'll just show you a little picture of what's going to happen. Somewhere here I'd have like 60 degrees. And I would expect that the temperature, if it was measured at 100, would be dropping off like this. And of course, it's not going to go down to 30 degrees because it would be colder than the room, right? It would have to warm up to the room temperature. So when we do it this time, what's decaying is actually this amount from here to there. What's the temperature we're losing? How many degrees is the coffee cup potentially going to erode? 40 degrees of temperature is what's going to erode, okay? And it can never go below 60. So I'm going to show you the equation if we were to solve it, and it'll make sense why the formula changes a little bit. So this becomes the current temperature minus 60, that's how much is left over to decay. When the temperature is 100 degrees, you'd have a full 40 degrees here to decay. When the temperature is now down to 70, you only have 10 degrees left. So this is telling me what my current difference is, because it's the difference that erodes. Right? So if I was to integrate these, I'd have dy over y minus 60 equals k dx. And if I integrate, I'm going to have, let's see here, natural log of y minus 60 equals kx plus a constant. And I'll do the e to the kx plus a constant equals y minus 60. So this time the model is going to look slightly different. Remember, this constant will come to the front and it will look like this. So here's my model now. Okay, this model is slightly different because I have this plus 60. Why did I have to add a plus 60? Aside from that I solved the differential equation to have it, why does it show up there? What is it about 60? It can't go below there. So once all of this has decayed and this has gone to 0, that's the asymptote for an exponential graph. So it should make sense that you should see a 60 degrees because it won't go below that in the temperature. The other thing is, now if we put in the information we were given that at time 0, it's 100 degrees. So now the constant equals 40. Why does the constant equal 40? Why should it make sense that my model is now this? This is the change in temperature. That's how much can decay, right? 40 degrees is how much this coffee cup is going to cool. And here's the function that's going to make it decay from 40 down to 0, right? So this is the model that I have to start with, which, again, if you use a bit of common sense, it's probably easier than writing it out as a differential equation over here to find the model. But either technique, if you were to come across this style of question, one of those is going to have to work for you. So it could be that you say, okay, well, I don't know, let's say instead, maybe we'll just quickly try this. Let's say, okay, got to pick a good example here. Okay, you take dinner, and dinner right now is, I don't know, what's reasonable temperature for food? 50 degrees? And you're going to put it in the freezer so you can take it to work the next day. And let's say your freezer is minus 4 degrees Celsius. You want to know what kind of a model would I start with here. So I'm looking for something that fits this pattern. Can anybody tell me maybe one thing that goes in here? Pardon me? So close, so close. Yeah, minus 4, right? There'll be a minus 4 in here because it's going to stop. It's not going to get any colder than minus 4 when you put it in the freezer. If you have such a freezer, please let me know and we'll be famous together. Okay? What else can we fill in? Why 54? That's how much the temperature of your dinner is going to change. So here's the model now that you're working with to find your continuous growth and decay. Okay, so the model can change, and the reason it changes is the asymptote's no longer 0. So that's kind of where you can throw a red flag up when you're doing a question, is if the asymptote wasn't 0, that would mess everything up. You'd have to look for a model like this. So let's try working out the end of this one, which says in 10 minutes, it's 90 degrees. Okay, so that'll give me my continuous growth rate. So let's see here. 30 equals 40 e to the 10k, and 3/4 is e to the 10k, so natural log 3/4 will be equal to 10k, so k is natural log 3/4 over 10. So that looks like about, we'll round it there. Okay, so that would be about my continuous rate of decay in this case. So if I want to know when's it going to be 80 degrees, I'll have to put all that into the model. So when does 80 equal to 40 e to the negative 0.029 t plus 60. So let's see here. 20 equals 40 e to the negative 0.29 t. And now I can start to use logs to figure out what that answer would be. So natural log of 1/2 equals negative 0.029 t. So t will be natural log of 1/2 over negative 0.029. So we would expect it's going to take about 24 minutes in order for it to hit the 80 degree mark.